Hello there, welcome to Learning Hub. Today, we're exploring a fascinating machine learning technique called Locally Weighted Linear Regression. It's a method that takes linear regression to the next level by adapting to the data locally instead of applying a single global model. By the end of this video, you'll understand what Locally Weighted Linear Regression is and why we need it, how it works, and how it differs from traditional linear regression. Plus, we'll break down the Python code step by step. So, let's get started. Linear regression is great when your data follows a straight line trend. But what happens when your data is more complex? Say, it curves or twists in unexpected ways. That's where locally weighted linear regression comes in. Instead of trying to fit one global straight line to all your data, locally weighted linear regression allows us to focus on smaller local neighborhoods. This is particularly used for nonlinear data when the relationship between features and target isn't a straight line and when different parts of the data exhibit different trends. Here's the big idea. Locally weighted linear regression assumes the world is linear but only in tiny patches. By stitching together these local patches, we can handle nonlinear relationships while still using simple linear regression as a building block. Now let's compare two approaches. Linear regression fits one single line or hyperplane to the entire dataset, assuming the relationship between input and output is consistent everywhere. Whereas locally weighted linear regression, on the other hand, fits a new local model for every prediction. It focuses on data points near the query point and assigns weight to each based on their proximity. Think of it like this. Linear regression is painting the entire canvas with just one brushstroke, while locally weighted linear regression uses small brushes to carefully paint every detail. Now, we'll see how this works. First of all, we're going to generate some synthetic data to test our algorithm. Here, we generate at least 100 random numbers around a mean of 10 with a standard deviation of 5. And then we calculate a cosine function for x, adding a small amount of noise to mimic the real world uncertainty. This gives us a wavy dataset, perfect for testing LWLR. Next, we organize our X or dataset into a design matrix. The extra column of ones allows our model to include an intercept term, shifting the predictions up or down as needed. Then, we write a main function that makes predictions using locally weighted linear regression. This function loops through all m data points and calls the local weight function to compute weights and make predictions for each data point based on its local neighborhood. Then, here we'll zoom into local weight, which does the heavy lifting. The weights W determine how much influence each nearby point has. The formula uses the least squares method, and this ensures that closer points have more influence on the prediction. After that, we calculate our weight matrix. The weights are determined using a Gaussian kernel. Here, the value of tau controls how far the model looks. Smaller tau means focusing on very close points, where larger tau widens the neighborhood. And finally, we run the model. We can try experimenting with different values of tau to see how it affects the predictions. Now, we'll see the implementation of this and then how it works. We'll start by importing some libraries. First of all, we'll import NumPy, and another library will be matplotlib. Now, we'll define a sigma value of 0.2. This will set the standard deviation for the noise to be added to our data later. Now, we'll define our data np.array, np.random.normal and 5 and 100. So what this will do is it generates 100 numbers following a normal distribution with the mean is 10 and the standard deviation is 5. After this, we're going to sort this. So this will sort the x values in ascending order to make the data easier to analyze or visualize later on. Now we'll define a function, func equals to np.cos x times np.pi divided by 3.5. So what this is going to do is, let me recorrect this. So this will apply the cosine function to the x values, scaled by a factor of pi by 3.5, which will result in a smooth oscillatory function based on x. What we're also going to do is we're going to create y based on this particular function, and then adding some Gaussian noise to this, which follows a normal distribution of mean 0 and deviation variance 0.2. so this is going to prepare y. We can see how the plot looks like. So x, y, then RO. So this is our data that we have. Further, we are now going to prepare our design matrix here. So x underscore mat equals to np dot matrix. We'll create this matrix from x. What this is going to do is convert the one-dimensional x array into a column vector or a matrix format, basically using numpy. Now the shape of x mat is going to be 100, 1. You can also check its shape. So I'm just going to extract m, which is going to be the shape value, or basically the number of elements in this particular matrix here. Here the m will result to 100. After this, I'm going to create a design matrix for linear regression by concatenating a column of ones in the original xmat column vector. So for that, xcon equals to np dot concatenate np dot ones, and this will be m comma 1, the comma, concatenate this in xmat, and the axis is going to be 1. So now if I print xmat, you can see, xcon, you can see that our design matrix is now ready. Actually it should not be like that. Oh sorry, I think I missed it here. So this is going to be this one. Let me run it from the beginning. Creating data, plotting will be the same. I'm just going to change the shape of it, and then xcon now should look like this. So basically this column of ones is for the intercept term in case of linear regression. Now after this, what I'm going to do is define this locally weighted linear regression function, which will take the input x, the design matrix, the target values, and the bandwidth parameter controlling the size of local neighborhood. So def LWR, it will take x, y, and then the bandwidth parameter tau. Now what we're going to do is initialize an array ypred to store the prediction for each point. So ypred is equals to np dot zeros, the size is m. After this, we'll loop over all data points for I in range m. Now we'll call the local weight function to compute weight and predictions for each point. So ypred equals to xi into local weight, and then we'll pass xi comma x, the complete data, y and tau to this local weight function. Whatever we have in ypred, we're just going to return this particular array of predicted vectors. Okay, now the next one, we're going to compute the locally weighted regression coefficient for a given query point xi. We'll define a function called local weight, which takes in the input xi, which is the current query point, the design matrix x, the target values y, and the bandwidth parameter tau. So def local weight input is going to be xi, comma x, comma y, comma tau. Now we'll compute the weight matrix using the funct function. So weight equals to funct funct. We'll pass xi, x, and tau to this one. Whatever we get here, we'll solve the weighted least square problem. So w equals to np dot linear algebra dot inverse x transpose into weight times x. Let me wrap this around with a bracket into x transpose into weight times y transpose. Now I'll return the regression coefficient w, so return w here. Finally, I'll create a function funct that computes a diagonal weight matrix for a given query point xi. So it will take input as xi, which is the current query point, x the design parameter, and tau the bandwidth parameter. So let me write this. The function is going to be def funct funct, pass xi, x, and tau. So first of all, we're going to initialize weight as an identity matrix, which means weights equals to np dot matrix, np dot mat, np dot I, comma m. Now for each data point, we'll calculate the weight based on its distance to xi using a Gaussian kernel. So for I in range m, diff equals to xi minus xi, and then the weights I comma 1 is going to follow np dot exp diff into diff transpose divided by minus 2 times tau square. So using this particular Gaussian kernel, I'm going to calculate the weight. Now I'm going to return this weight, so return weights. Okay, this is done too. After this, I'm going to convert the y array into a matrix format for compatibility with matrix operation in the locally weighted linear regression implementation. So y mat equal to np dot matrix y. We'll keep the tau as 0.5, the bandwidth parameter as 0.5, and then we'll call y predicted function. So y predicted equal to LWLR. We'll pass our design matrix, the y matrix, and then tau here, and then get our predictions. Okay, so the code is ready. We'll try to plot our actual points RO, and then we'll also plot the locally weighted linear regression line here. So let's plot it using k minus, and then if we see this, so here y pred I equals to xi into local weight. So rerun this, pass the code again, we get y predicted, and then when we plot this, we get a locally weighted linear regression plot here. This is I comma I. Sorry, I think I made a mistake here. This should be I comma I. If I reload this, then I see that a line has been plotted, or a curve has been plotted to kind of fit our data into this particular plot. Let's change the value of tau here, and then so if we change this value to 0.8 or maybe 0.5, then we see that that the point kind of generalizes more in this particular case. So This is all about locally weighted linear regression and its implementation here. So here's the result. A beautifully smooth curve that adapts to the data thanks to locally weighted linear regression. So to summarize, locally weighted linear regression handles nonlinear patterns by building localized models. It's different from linear regression because it doesn't assume a global trend, and it's simple yet powerful, especially for datasets with varying patterns. Thanks for watching. If you found this video helpful, don't forget to like, subscribe and share. See you in the next video. Thank you.